Welcome back, team, to another video. This one's going to be serving as the purpose for the solutions to the first piece of the homework assignment for chapter 17. In these practice problems, or in this assignment, I'm actually going to be posting the solutions to them online. I am going to go through a couple of them just to explain a little bit of the nuances so you can hear me explain them a little bit. However, I found the solutions, so I want to go ahead and just give you those instead of making a video series for all of the solutions. So hopefully you can learn independently a little bit more during this time. But for today, I'm going to go over some of the answers for us. So let's start talking about number one. Number one was all about looking at Bernoulli's trials. And so before I start answering some of those questions, one question, I actually want to reiterate and review what a Bernoulli trial actually is. In order for something to be called a Bernoulli trial, you need three things that need to be satisfied. The first is that there's only two possible outcomes, which means the probability of one trial doesn't affect the probability of the other trial. Finally, the third piece to this that I want to add, it may be a little bit similar to the idea of independence, but it's more explicitly in regards to a Bernoulli trial needs to have a constant probability of success. Most of the time this is satisfied by it being independent because one probability does not affect the probability of something else happening. But we really need to make sure that the probability of something occurring doesn't change throughout. We need to keep it the same even if they're independent, and we need to make sure that the probability of success is going to remain the same throughout every single trial. For the purpose of number one, I specifically want to talk about part C. Part C discusses the importance of dealing cards. In fact, it says they want to deal 7 cards from a deck. And it wants us to determine whether or not it's a Bernoulli trial to get all hearts in that scenario when we deal 7 cards. Now, this trial is not a Bernoulli trial. It is not a Bernoulli. And let's talk about the reasons why. First off, are there 2 possible outcomes? Yeah. It's either all hearts or not all hearts. So the first condition here is correct. So yeah, technically that could be Bernoulli. Number 2, trials need to be independent. It is not independent because when we deal cards, we don't deal a card and then put it back into the deck and then deal it again. We're dealing a card and we're leaving it out. So if I deal a heart, the odds of me getting a heart the next time is going to change. Every time I deal a card, the probability is going to be different. While independent, if we replace, the probabilities are not constant. Therefore, no independence can be satisfied. It is not a Bernoulli trial. Most of the other examples are a little bit easier to look at. For example, for part D, we're actually looking at a budget proposal. And here, they're actually looking at a poll of 500 of the 3,000 likely voters to see how many would be in favor for the proposed budget. This problem is actually not considered Bernoulli. Remember, this isn't the actual proposal. This is just a survey to see who would vote or who would approve. It's a poll. Now, the problem with the poll is, number one, is satisfied for a Bernoulli trial because there are 2 possible outcomes. It's either they approve or not approve. So that's good. But when we're giving a poll or giving a survey to somebody, if we don't put them back into the population to have an equal chance of getting selected again, we are either increasing or decreasing the chances of somebody either approving or not approving. Everybody in the population of the 3,000 voters have an opinion. They either approve or disapprove. So similar with the deck of cards, if I select 500 of them, that would yield a certain probability. But if I don't put them back into the population each time I select a person to poll, I lose my independence. So number 2, it is not independent. While number 1 focused on the Bernoulli trials and essentially what makes up a Bernoulli trial, the rest of the problems deal with a little bit of the binomial and the geometric distributions that we want to focus on. But let's talk about number 3. Number 3 confused a lot of students, and we're going to zip through it a little bit, but explain kind of what it was looking for and the expectations set forth. Number 3 was all about simulating a model. I'm going to call it a simulation. And if you remember simulations, back when we discussed them in a previous unit, we have to first identify what it is we're simulating. In this case, we're looking at the number of cereal boxes to open until we get a Tiger Woods card. If you remember us doing this earlier, we did this, but instead of a Tiger Woods card, we actually used teachers' names. In this case, if we are looking for a Tiger Woods card, what kind of model do you think we'd be actually running? A binomial or a geometric? Well, that's something that we're going to talk about in just a second. To initiate this problem, however, Part A asks us to describe how you would simulate the search for Tiger Woods using random numbers. Well, in this problem, it actually states that the probability of us pulling a Tiger Woods card is 20%. It's actually in 20% of the boxes. So P is going to equal the probability of a cereal box containing, I'm going to put TW, Tiger Woods card. In this case, the probability is actually 20%. So if you recall, in the last unit, if we wanted to run a simulation, we had to first identify how to model it. In this case, I'm going to use the numbers 0 through 9. And I'm going to make 20% of them equal a Tiger Woods card. In this case, 20% is 1/5. So the numbers 0 and 1 are going to represent a Tiger Woods card, or a Tiger card. The rest is going to be not a Tiger card. In order to run this simulation, I would use a random digit table comprised of a bunch of random digits and determine when one of these numbers come up, it mimics us opening a cereal box and pulling out the card. For example, if I use the numbers 0, 3, 5, 6, 7, 7, 9, 8, 1, 2, 3, 6, 8, 7, 1, just call those random digits, I can go through each of them and see whether or not I'll get a Tiger card. For example, first pull, a Tiger Woods card. But then I would not get a card, 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 not get a card. Oop, I found another one. So in 9 different trials, I would find about 2 Tiger Woods cards. Or in fact, 10 trials, I would find 2 Tiger Woods cards, which is also about 20%. Part B actually asks you to run this simulation 30 times. Here we did it 10. You can do it a couple more if you'd like. Part C then asks you to estimate the probability. In order to estimate the probability, you would take the total amount of trials, the amount of successes that you'd have, and then you divide it to estimate, what's the likeliness of me pulling a Tiger Woods card? So for Part C, the answers will vary. Part D is where it gets interesting to us, which wants a probability model or a distribution. In other words, what the problem is asking us to do is to actually make a probability table, to make a table of what's going on here. In order for us to make a table, we need to identify what it is we're doing. Here, we're trying to identify how many cereal boxes we need to open until we get a Tiger Woods card. So in this case, the number of cereal boxes to open will represent a value we're going to call X. So when we make a table, our X value is going to represent the number of cereal boxes we need to open in order to get a Tiger Woods card. The probability of X will be the odds of us pulling a Tiger Woods card after that many cereal boxes. So if we take a look at this problem, we just care if we get a Tiger Woods card. We want to know what are the likeliness of us getting our first Tiger Woods card on X number of boxes that we open. So this probability model is actually a model of the geometric probability in order for us to determine how to find our answers. We'll go through that in a second. Because a geometric model can go on forever, theoretically we can open hundreds of cereal boxes. It'd be nice for us to stop after a certain time. In this case, we'll go up to 5. 1 box, 2 box, 3 box, 4 box, 5 boxes. I'm going to say 5 plus boxes. In order to fill out this table, we need to determine what's the likeliness of us pulling a Tiger Woods card out of 1 box. As the problem originally stated, it's actually 20%. There's a 20% chance that that box actually has it. Here's the problem when we move forward in this probability distribution. Here it says, what's the likeliness of me pulling a Tiger Woods card after 2 boxes pulled? That means that we did not pull a Tiger Woods card on the first box, but then we did pull a Tiger Woods card on the second box. So, if we do the math here, we have a 0.8% chance of us failing and not pulling it, multiplied with a 0.2% chance of us actually pulling it. If we continue this route, we'll notice that the third box that we open is the box that we want to be our success, which means we fail 2 times before that success actually happens. So we have 0.8 2 times multiplied with me succeeding finally on the 3rd time. We can continue. We have 0.8. For 4 boxes, we fail 3 times. And then a 0.2% chance of us succeeding the next time. In order for us to figure out what goes in this 5th box, yes, you can do 0.8 to the 4th power multiplied by 0.2. However, we're doing it for 5 plus boxes, which means we should add up these values and then subtract that by 100% in order for us to figure out what's the likeliness that I'll get it past 5 boxes. I'm not going to do the math for that right now. It just wants you to set up the model for it. Part E wants you to describe the difference between this model and the solutions we get for the estimation of us pulling a Tiger Woods card and what we did here for the simulation. But for the purpose of this practice problem, it's okay if we didn't get to that point. This is what we're going to need moving forward as we start understanding the geometric model.